Today we are solving maximum width of a binary tree. Given the root of a binary tree, we need to return the maximum width of the given tree among all the levels, where the width of one level is defined as the length between the end nodes, where these end nodes have to be non-null nodes. To find out what exactly are these null nodes, we need to compare this tree with a complete binary tree, where in a complete binary tree, each node except for the leaf node is supposed to have two child nodes. In this example tree, we notice that node C is missing a child, and this missing child is the null node. This node cannot be the leftmost or the rightmost child in that level. But if it's in between the non-null nodes, like here, it can definitely be counted towards the width. So the width at each level for this tree is at level 1, width is 0 because there is only one node. We need at least two nodes to calculate the width. For level 2, there are two nodes, so the width is 2. For level 3, there are three nodes, but there is a missing node as well, so the total width of level 3 is 4. And we need to return the maximum width among all the levels, which is 4 from level 3. So we return 4. Let's look at another example. Here is a different example. To find the width at each level, we have to first convert this tree into a complete binary tree. This is the complete version of the same tree. So the width at level 1 is 0 because there's only one node. Width at level 2 is 2, level 3 is 3, and level 4 is 7. We did not use the null node over here because the leftmost and the rightmost nodes has to be non-null nodes. So we can get rid of this null node at the bottom right. And we return 7 because that's the maximum width. Do we really have to convert the given tree into a complete binary tree before we could calculate the width at each level? No, because all we need is the count of the non-null nodes, hence we do not have to convert the given tree into a complete binary tree. How do we get the count of the null nodes at each level? To find out, let's number these nodes starting from 0 at the root node. If we take a closer look at these indices for nodes, we can notice a pattern. Index of the left child is 2 times the index of the parent plus 1. And index of the right child is 2 times the index of the parent plus 2. We can verify this for any other node in the tree. Index of this node is 2 times 4 plus 1, and index of this node is 2 times 5 plus 2. Once we have these indices, it's easy to find the width at each level. All we have to do is index of the rightmost node in that level minus the index of the leftmost node in that level plus 1, which is 4. I apologize for the typo here, this should have been 4. At level 4, index of the rightmost child is 13 minus 7, which is the index of the leftmost child, plus 1 gives us 7. Let's try to apply this relationship in the original tree and look at the indices again. Let's go back to the original tree. Here is the original tree again. Let's apply this formula to this tree. We start with index of 0 for root node. Index of left is 2 times 0 plus 1, which is 1. Index of right is 2 times 0 plus 2 is 2. And we repeat the same. Index of left is 2 times 1 plus 1, which is 3. Index of the right is 2 times 2 plus 2 is 6. Index of left is 2 times 3 plus 1 is 7. Index of left again is 2 times 6 plus 1 is 13. So to calculate the width at each level, all we have to do now is index of the rightmost child minus index of the leftmost child plus 1. So 2 minus 1 plus 1 is 2. 6 minus 3 plus 1 is 4. 13 minus 7 plus 1 is 7. And we return 7. So to solve this problem, we can apply breadth first search starting from level 1 and process these nodes level by level. At each level, we calculate the width by getting the index of the rightmost child minus leftmost child plus 1. And we repeat the same for all the levels. So the runtime complexity of this approach will be O of n because we'll be adding each node once to the queue and we'll be popping the same node once out of the queue. The spacetime complexity is also O of n because in the worst case, we'll be adding all the nodes to the queue. Let's write the code for this algorithm. Let's initialize the max width to 0, and we have to do breadth first search starting from the root node. Let's add root node to the queue, root, and index of the root node we start with is 0. While the queue is not empty, we process all the nodes at this level. So let's call this length of this level is length of the queue. To calculate the width at this level, we need the index of the left node, which is always the first element in the queue at that level. So left index is the first element of the queue. This one. Now we go through each and every node in that level. Let's go in range length of the level. We pop the node and its index, let's call this right index queue.pop from the left of the queue. Let's update the max width if the new width is greater than the previous width. The new width is right index minus left index plus 1. Next, we add the child nodes to the next level. If the node has the left child, we add that to the queue node.left, and the index of this node will be index of the parent node, which is right index, into 2 times plus 1. We do the same if there is a right node. We append node right, and the index of the right node will be right index, which is the index of the parent, into 2 plus 2. And we repeat this for all the levels and finally return max width. Oh, there is a typo here. Let's fix the typo. Let's try to run this code. The submission goes through. If you found this video to be helpful, please support by liking the video and subscribing to the channel. And I will see you in the next video. Thank you.